Chapter 7 was a short chapter regarding eigenvalues and eigenvectors and some of the properties involved with both of them. What I did on this first page was list the terms that we used. We talked about eigenvalues, eigenvectors, and consequently we also talked about what were called eigenspaces, which basically was if one eigenvalue was associated with more than one eigenvector. Talked about the characteristic equation and the polynomial, which was used to find the eigenvalues. And the characteristic polynomial is a minus lambda I, that determinant. And then the equation is when you set that characteristic polynomial equal to 0. So that's used to find the eigenvalues, and then once you have the eigenvalues, you use the fact that a minus lambda ix equals 0, and set up an augmented equation to find the corresponding eigenvectors. Diagonalizable means that we can find a matrix P such that P inverse AP equals a diagonal matrix. And orthogonally diagonalizable means you can find a matrix P such that P transpose AP equals a diagonal matrix. So if you notice the association between these two, that means P inverse equals P transpose, which from our last chapter meant that P had to be what's called an orthogonal matrix. Over on the right, it has some of the properties involved. So if ax equals lambda x, then we have the property a to the nx equals lambda to the n in inverse, and so on and so forth. We were also able to calculate the determinant and the trace knowing the eigenvalues. So for example, if I know that lambda equals 3, in a particular matrix, then I can say that if I have a cubed plus a inverse plus 3ix, or 3i, the corresponding eigenvalue for that would be lambda cubed, would be would be 3 cubed plus 1/3 plus 3. Of course, assuming that A inverse actually exists. So what I'm going to do is just go through my examples, calculating eigenvalues, eigenvectors, and restating the properties that come up. This one's just a 3x3 matrix, so I'm just going to go through how to find the eigenvalues and corresponding eigenvectors for it. So first I'm going to solve the characteristic equation, which means finding when the determinant 2 minus lambda, 1, 1, 0, 3 minus lambda, 1, 0, 1, 3 minus lambda equals 0. Now this is already set up nicely to do just a expansion along a column. I'm going to use column 1 since it has all those zeros there. And so the determinant for this would be 2 minus lambda multiplied by the corresponding cofactor, which would be 3 minus lambda, 3 minus lambda, minus 1. Excuse me, minus 1. Equals 0. So 2 minus lambda, multiplying this out, I get lambda squared minus 6 lambda plus 8 equals 0. Factoring 2 minus lambda, lambda minus 4, and lambda minus 2 equals 0. So I have two eigenvalues, lambda equals 2 and lambda equals 4. Now I'm going to set up the corresponding augmented matrices that I would use to solve for the eigenvectors. So basically, remember, I'm solving a minus lambda ix equals 0. So let's start with our first case, lambda equals 2. If I set this up, I'm going to have 0, 1, 1, 0, 1, 1, 0, 1, 1, and augmented with 0, 0, 0. So RREFing this reduces down to 0, 1, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0. And again, if I read this as a solution, that means that x2 equals negative x3, and it means that x1 can be any real number. So my corresponding vectors would be 1, 0, 0, and then since x2 can equal negative x3, 0, negative 1, 1. Now if I do likewise with lambda equals 4, going back to my original, If I put in lambda equals 4, I get negative 2, 1, 1, 0, negative 1, 1, 0, 1, negative 1. And again, augmenting this with 0, 0, 0. So REFing this, I get, let's see, if I add row 1 plus row 2, I'm going to get negative 2, 0, 0. And obviously the last two I can reduce to 0, 1, negative 1, 0, 0, 0. Augmented with 0, 0, 0. And I get, for the solution, this time x1 equals 0, x2 equals x3. And my corresponding eigenvector then is 0, 1, 1. So notice these eigenvectors are linearly independent of each other. And they all span R3. So that means that this particular matrix is diagonalizable, and I can define the corresponding P and the corresponding diagonal matrix. So if I were to continue, P would then equal something like, let's do it this way. 1, 0, 0, 0, 1, 1, 0, negative 1, 1. And if I were to do P inverse AP, the corresponding diagonal matrix, now I need to make sure my eigenvalues are in the same order diagonally. So the first eigenvalue would be 2, 0, 0. The next one would be 0, 4, 0. And the last one would be 0, 0, 2. So P inverse AP. Consequently, that also means that I can rewrite A as TDP inverse. So I could rewrite A as 1, 0, 0, 0, 1, negative 1, 0, 1, 1, D, 2, 0, 0, 0, 4, 0, 0, 0, 2, and P inverse. 1, 0, 0, 0, 1, negative 1, 0, 1, 1. Now I'm going to expound on some of the other properties that this means. A squared, for example, would equal PDP inverse, PDP inverse, P inverse. But notice these become the identity matrix, so this would become PD squared P inverse. And so I could rewrite that as a product of 1, 0, 0, 0, 1, negative 1, 0, 1, 1. The middle would be squared, 4, 16, and 4. And then the last one, this is P inverse. 1, 0, 0, 0, 1, negative 1, 0, 1, 1, inverse. Another property that comes up from this, if I take the determinant of A, I get the determinant of P times the determinant of D times the determinant of P inverse. But these two equal 1, so the determinant of A equals the determinant of D. But the determinant of D is 2, 0, 0, 0, 4, 0, 0, 0, 2. And if I take the determinant of that, it equals 16, which is the product of the eigenvalues. And if you go all the way back up here, if I were to actually take this determinant, let's just do it the old-fashioned way, I would get 2 times 9 minus 1, which is 16, and that checks out. The trace of this is the sum of the diagonal elements, which would be 2 plus 3 plus 3, which is 8. And notice down here, the trace of A, if I add up my eigenvalues, lambda 1 plus lambda 2 plus lambda 3, is also equal to 2 plus 4 plus 2, which equals 8. So just as an example, it confirms the property involved with the determinant of A and the trace of A. All right, let's do another matrix. I have 3 here that we're going to go through. So this one here, and again, I'm going to go through the characteristic equation. So 3 minus lambda, 4, negative 1, negative 1, negative 2, minus lambda, 1, 3, 9, and negative lambda. Now, for this one, I'm actually going to do some row operations to help simplify it. So for example, I could do, well, let's cancel out these ones here. So I'm going to do row 1 plus row 2. And if I do that, I'm going to end up with 2 minus lambda, 2 minus lambda, 0, negative 1, 2 minus lambda, or sorry, negative 2 minus lambda, 1, 3, 9, negative lambda. Now remember, we can also do some factoring. So I'm going to factor 2 minus lambda out of row 1. And I'm going to have 1, 1, 0, negative 1, negative 2 minus lambda, 1, 3, 9, negative lambda. I think I might stop there. Now you can continue, like you could do a row 1 plus row 2 if you want, but the whole idea is to try to get this into something that you don't have a cubic to work with. And at this point, if I were to do 2 minus lambda times the resulting determinant, and in fact I'm going to use row 1 since there's a 0 there, I'll have a quadratic that I need to solve instead of a cubic that I need to solve. So the determinant for this would be 1 times negative lambda, negative 2 minus lambda, minus 9, minus the next determinant, which is going to be lambda minus 3. Okay, so I'm going to just keep going through the algebra here. 2 minus lambda, this is going to become lambda squared plus 2 lambda minus 9 minus lambda plus 3. 2 minus lambda, lambda squared plus lambda minus 6. 2 minus lambda, and then factoring this, lambda plus 3, lambda minus 2. So my eigenvalues are 2 and negative 3. Now, the one I want to focus on is lambda equals 2. So I'm going to come all the way up here and do my lambda equals 2. If lambda equals 2, then the augmented matrix I'm going to solve is 1, 4, negative 1, negative 1, negative 4, 1, and 3, 9, negative 2. And I'm going to augment that with 0, 0, 0. So let's see. I'm going to do R3 plus 3R2. And I'm going to move it to the top. So that's going to be 0, negative 3, and 1. And I have a 1, 4, negative 1. The other one cancels out. So I have 0, 0, 0. And then let's see. If I do a row 2 plus row 1, and then move that, I'm going to have 1, 1, 0, 0, and then this becomes 0, negative 3, 1, 0, 0, 0, 0, 0. So I have x2 equals negative x1, and x3 equals 3x2. So let's make this x1 equals negative x2. So the corresponding eigenvector is going to be x1, which equals negative x2, x2, and x3, which equals 3x2, which means I have negative 1, 1, 3 as my eigenvector. But notice lambda equals 2 had a multiplicity of 2, and I only have one eigenvector, so that means this is not diagonalizable, because if I try to make the matrix P, it wouldn't be a square matrix, because I would only have 2 eigenvectors, even though I have 3 eigenvalues that correspond with it. And that's all I wanted to show with the second example. Third one, I want to diagonalize this, which is a really easy matrix, at least in terms of the elements. But one thing I want to mention is that this is symmetric. So A transpose equals A, which means we should be able to orthogonally diagonalize this. Orthogonally diagonalized means I should be able to come up with an orthogonal matrix P transpose, such that P transpose equals P inverse, and P transpose AP equals the diagonal matrix. So once again, I'm going to go through the characteristic polynomial and show you the corresponding eigenvectors. So 1 minus lambda, 1, 1, 1, 1 minus lambda, 1, 1, 1, 1 minus lambda equals 0. Same thing, I want to do some row operations with this. So let's do row 3 minus row 2. And the whole idea is I want to get at least 1 0 in there, so it makes it a little bit easier to calculate the determinant. So 1 minus lambda, 1, 1. 1, 1 minus lambda, 1. 0, this will be lambda, and this will be negative lambda. So same thing, I'm going to factor a lambda out of row 3, and I will have 1 minus lambda, 1, 1, 1, 1 minus lambda, 1, 0, 1, negative 1. And now if I expand along row 3, I'll have lambda. I'm going to expand along this row here. And the resulting one, let's see, plus minus plus minus plus. Wait, plus minus plus minus. So this will be negative 1 times the corresponding determinant, which is 1 times 1 minus lambda minus 1. And then minus 1 times the corresponding determinant, 1 minus lambda squared minus 1. Oh, so how about I factor a negative 1 out loud? So it'll be negative lambda, 1 minus lambda minus 1 for the first part, plus 1 minus lambda, plus 1 minus lambda squared minus 1. I'm going to keep going with the algebra here. So negative lambda plus 1 minus 2 lambda plus lambda squared minus 1. Negative lambda, lambda squared minus 3 lambda equals 0. Negative lambda, and then another lambda, and then lambda minus 3 equals 0. So my eigenvalues are lambda equals 0 and 3. Okay, corresponding eigenvalues. Let's start with lambda equals 0. So if I use lambda equals 0, I get 0, 1, 1, 0, 0, 1, 0, 1, 0, 0, 1, 1, 0, 0, sorry. And so if I RREF this, let's see, so let's do row 2 minus row 3, and let's move that to the top. So that'll be 1, negative 1, 1, 0, 1, 1, 0, 0, 0, 1, 1, 0. Kind of moving things around. So now I'll do row 2 minus row 1, 0, wrong one. So 1, negative 1, 1, 0, 0, 2, negative 1, 0, 1, 1. I'll do row 2 minus 2 row 3, and while I'm at it, row 1 plus row 3. So 1, 0, 2, 0, 0, 0, negative 3, 0, 0, 1, 1, 0. And I think I messed up. Actually, I did. I know I did. Sorry about that, folks. I just realized I got carried away. So lambda equals 0, not lambda equals 1. So if I do lambda equals 0, it's actually a lot easier. I apologize, because lambda equals 0 would just be 1, 1, 1, 1, 1, 1, 1, 1, 1, 0, 0, 0. And so if I RREF this, I just have 1, 1, 1, 0. I need something that's not looking good. Okay, so that means x1, for example, equals negative x2 minus x3. So the corresponding eigenvectors would be negative 1, 1, 0, and negative 1, 0, 1. Now, if I do lambda equals 3, I'm going to have negative 2, 1, 1, 1, negative 2, 1, 1, 1, negative 2, augmented with 0, 0, 0. And this RES2, 1, 0, negative 1, 0, 1, negative 1, 0, 0, 0, 0. So this one you get x1 equals x3, x2 equals x3, and so the corresponding eigenvector is 1, 1, 1. Now, remember that I'm trying to come up with an orthogonal matrix. So if you look at these vectors here, they are linearly independent, but they are not orthogonal to each other. Because if I dot product those two, I don't get 0. I don't get 0. So that means I've got to do a Gram-Schmidt with them as a result. Gram-Schmidt, let's let V1 equal negative 1, 1, 0. And then V2 will make it equal to negative 1, 0, 1 minus the projection of negative 1, 0, 1 onto negative 1, 1, 0. So that's going to equal negative 1, 0, 1 plus, no, minus, let's see, that's going to be 1 over the magnitude of this, which is 2, times negative 1, 1, 0. So if I put that together, I get negative 1 plus 1 half, which is negative 1 half. I get 0 minus 1 half, so negative 1 half, and I get 1. I'm going to rescale that just so it's easier for me to look at. So I'm going to make this into negative 1, and 2. And now notice this one and this one. Which one am I looking at? This one, negative 1, and 2. And this one, my original one, are now orthogonal to each other. So I can define my P. P has to be an orthogonal matrix, which means the columns are orthogonal to each other, and they all have a magnitude of 1. So, for example, for this one, I'm going to use negative 1 over root 2, 1 over root 2, and 0 for the first one. And then I'll use 1 over negative 1 over square root of 6, negative 1 over square root of 6, and 2 over square root of 6, normalizing the next one. And then I'll use 1 over square root of 3, 1 over square root of 3, and 1 over square root of 3 for my last one. And now this is an orthogonal matrix. And if I do P transpose AP, I'm going to get a diagonal matrix. And the diagonal matrix would have the eigenvalues 0, 0 for the first two, and then 3 for the last one. So there's an example of orthogonally diagonalizing a matrix. Now I want to just do some quick properties to review that as well. So A is a 2 by 2 matrix such that A squared equals I, and I want to come up with eigenvalues for x, x plus ax, and x minus lambda x. So let's start from the beginning. Now I think I'm going to have to do some of these in general. So for example, for any vector x, that would be ax equals lambda x. But now I'll go ahead and work on the next two. So if x plus ax is an eigenvector A, that means A times x plus ax has to equal some eigenvalue. So let's call it lambda 1 times x plus ax. Now if I expand this out, I'm going to get ax plus a squared x equals lambda 1x plus lambda 1ax. But I have a couple of properties. For example, ax equals lambda x. So I'm going to go ahead and put that in. A squared equals I, so that's x. Lambda 1 x plus lambda 1 lambda x. And now I just have an equation that I have to use to solve for x. So I get lambda plus 1 x equals lambda 1 plus lambda 1 lambda x. Lambda plus 1 x equals lambda 1 1 plus lambda x. But if these two equal each other and x is non-zero, that means that lambda 1 has to equal 1. Same idea here. Let's say I have ax minus ax equals lambda 2 x minus ax. If I expand this out, I get ax, which equals lambda x, minus a squared x, which is, but a squared is I, so that's just x, equals lambda 2x minus lambda 2 lambda x. That means lambda minus 1 x equals lambda 2 1 minus lambda x, or lambda minus 1 x equals negative lambda 2 1 minus lambda x. So that means negative lambda 2 has to equal 1, and lambda 2 equals negative 1. Lastly, I want to just remind you how to put together some matrices using visual eigenvalues and eigenvectors. Oops. So let's start with this one. Reflection about y equals negative 5x. So visually, if you have y equals negative 5x, you can imagine you've got two eigenvectors. One, if the eigenvector exactly on the line, so that would be if the eigenvector was something like negative 1, 5, then it would reflect exactly onto itself, so its lambda would be 1. If I were to take something perpendicular, so that would be something like negative 5, negative 1, it would reflect to its opposite, and so its eigenvalue would be negative 1. Now, since A equals PDP inverse, P consisting of eigenvectors and D consisting of eigenvalues, I can write this as a product of three matrices, negative 1, 5, negative 5, negative 1. That would be my P. My D would be the corresponding eigenvalues, so 1, negative 1. And notice these are matched up. And then P inverse, negative 1, 5, negative 5, negative 1 inverse. So likewise, I could do the same with the projection. So imagine I have a plane here. If I were to take the normal vector, it would project to 0. So the normal vector is 2, negative 3, 5. Oops, sorry, this needs to be a 0. And then the eigenvalue for it would be 0, because the normal would reflect to the 0 vector. If I take two vectors on the plane, they would reflect to themselves. So I need 3 points. Now, 0, 0 is a point on the plane. And then if I take something like 3, 2, 0, that would be a point on the plane. And if I take something like, let's see here, how about negative 5, 0, 2? That would be another point on the plane. And so these would create the vector 3, 2, 0. These here would create the vector negative 5, 0, 2. So I could write A equals PDP inverse 2, negative 3, 5, 3, 2, 0, negative 5, 0, 2. The corresponding eigenvalues, which would be 0, 1, 1. These have an eigenvalue of 1. 0, 0, 0, 0, 0, 0. And then P inverse. 2, 3, negative 5, negative 3, 2, 0, 5, 0, 2. Good luck studying for the test next week.